Welcome back, folks. Before we start to build more complicated circuits and we can talk about the other two fundamental laws of circuit analysis, we got to go through what I sometimes call a vocabulary lesson, but we could just as easily call it an anatomy lesson. Like, what are the parts of a circuit? And we need language to talk about how things are connected, how they're related to each other in the circuit, because that's gonna help us analyze the circuit. Okay, we want to be able to analyze any circuit at the end of this. So let's go through this little vocabulary slash anatomy lesson, and at the end of that, we'll be able to start putting things together in more complicated ways. Okay, so here's your anatomy lesson. So the first thing that we have to talk about is when we connect two components together. Okay, and we're going to call that a node in the circuit. And a node, let's see, any point in a circuit where two or more elements are connected. Two or more elements are connected. Okay, and what that's going to look like in a schematic, it could look at any number of ways. Let's see, we got our resistor here, and we're going to connect it to another resistor here. Then this point in between is called a node. Okay, now we can add to it, we can do other things, we can have other components in here, and we can connect another resistor down there. It's still just one node, and now we have the or more part of two or more elements connected together. Okay, we connect them together. Now physically what this means is you twist some wires together, or you stick the legs of components into a breadboard if you're prototyping. You can use screw terminals, anything like that. Anytime you take two circuit elements and you make them one and you have them conduct between the two, you're creating a node. And this is kind of the most fundamental piece of a circuit. Okay, everything's going to be built out of nodes because we're connecting things together. Okay, so important fact about a node is the voltage. As far as circuit analysis is concerned, voltage at all points on the node is the same. Node is equal. Okay, and that means it's equal when measured against the same reference, right? So we're talking about ground now. So if we were going to do that in the lab, we're not going to do that in the lab right now because we're virtual, but we would have some probes. Let me go grab some probes. Okay, some props I do have here, maybe not the same ones we'd use in the lab, but I do have a multimeter, and if I wanted to measure voltage, it comes complete with a black and a red probe. I'll try to get it in front of my shirt so that you can actually see it. Okay. You know what? Let's get big for a second. Hey, I'm back. Okay. So this is a pretty cheap multimeter that I just carry around in my toolbox here. But if I wanted to measure voltage, I can go ahead and set it to measure some range of voltage, and then I'm using these two probes to measure voltage. Now I'm going to use the red probe to measure voltage at a particular node, and I'm going to use the black probe to connect to my reference point. So if there's a ground in the circuit, I would probably connect the black to the reference. And as long as I connect these, okay, so these kinds of probes that we'd find in a multimeter, to measure that, let's put that there. Then let's get back to our picture here. Okay, the black probe is connected to ground somewhere. If I put the red probe over here, or if I put the red probe over here, I'm going to measure the same voltage. Okay, it doesn't matter. It's only when I cross over a component that I'm going to see a change in voltage. We call it a voltage drop or a voltage rise, depending on whether it's going up or going down. Okay, but if I stay on the same node, the voltage is always the same. Okay, so that's a node. This next bit of vocabulary I take issue with. I've looked at a lot of textbooks. It's called the branch, and it's a little sloppier because I think it needs a little more qualification. You can't just say how many branches are in a particular circuit. But let's start out with a circuit. So I'll stick a battery over here and a resistor. Okay, and I'll put 2 resistors here. Okay, so a branch is defined as any current path between 2 nodes. Okay, and if you leave it at that, you might be okay. The first thing I'm going to ask you to do with a circuit that I usually do on the board, and I call you up and I embarrass you, you're going to have to do that at home all by yourself. I'm depending on you. The first thing I ask you to do is figure out how many nodes are in this circuit. All right. If I don't need to cross over a component, actually this might work out better virtually. If you don't need to cross over the component, it's the same node. You haven't moved to a different node. So as I look at this circuit, let's get some different colors here. And you think of it as like flood fill, right? If you're using paint, let's see if I can do this. This is all one node because I haven't crossed over a component yet. Okay. All of that is one node. All the way over here, it's all the same node. Okay. All of this, try to make it blue. Always blue, always blue. Okay. That's all one node. I didn't cross over a component anywhere. That's one node. So some people get trapped and think that this is a node and this is a node and this is a node, but it's all the same node. Okay. We can play the same game down here on the bottom. If I start at this component, the bottom of the battery, the negative terminal of the battery, and I fill all of this in, okay, this is all one node down here. I haven't crossed over a component yet. Okay, until I hit that. That's all one node. Okay, now if you're really paying attention, so invariably somebody will raise their hand and say 2, and I'll go, that's great, thanks for participating, but you're wrong. And that's okay, because that's the point of this exercise, is to find the other node. There's another node right in here. Okay, so there's 3 nodes in this particular problem. 3 nodes in this circuit. We'll do more complicated ones, but you have to be able to identify the nodes before you can analyze the circuit. Okay, so it's a good exercise, but what we really want to talk about is branches. So how many branches in this circuit? That's the next thing. The naive answer is 3, and you can say, well, there's a current path here, here, and here, but then things get sloppier when you say, well, there's this node here, and what do they mean by any current path between 2 nodes? Well, between the green and the blue, there's a current path through this one resistor here, and between the green and the red, there's a current path between the green and the red through this resistor here. All right, so it's a little messier, and I think what you need to talk about when you're talking about branches is we need to specify which 2 nodes we're talking about. Okay, because it turns into a matter of perspective when you're looking at branches. Okay, the method of analysis that I don't teach is called branch analysis. It doesn't scale well. It works okay for small circuits, but then it very quickly gets out of hand with anything that's more complicated. But you will hear the word branch. I'll use it. And what we're talking about is, well, some of the current's going to flow here, some of the current's going to flow here, some of the current's going to flow through here, as we look at the current flow between the blue and the red nodes. Okay, between the blue and the green, it's only going to flow through that resistor because there's only one branch between those nodes. So that's branch. One of my, it's a sloppier word in my opinion. Like I said, I've scoured textbooks from all different people, and I haven't found a good definition of it yet that's any cleaner. But it is talked about, so you need to know it. Okay, next one. These next two are related to each other, and there's a very subtle difference, and it's important to understand that difference so that when I say a word, you know which one we're talking about, because they can't be used interchangeably. Okay, a loop, any closed path in a circuit. Okay, and we're going to begin and end at the same node. Begin and end at the same node. And we generally try to avoid figure eights. I don't think that's... well, okay, so avoid, rather than figure, avoid passing through same node twice. Okay, so the circuit's going to be, well, it's going to be a little crazier. So who's looking forward to that? So we're going to make up a circuit. I'm going to do it in white, which I don't use as often. Okay, that's not white. Let's grab white over here. But I am going to draw it. Okay, so let's stick a battery here. Okay. And a bunch of resistors sticking out here. Another one down here. Down there. And over there. Okay, I said we're going to be building more complicated circuits. I think this one's working pretty well. All right, before we talk about loops, I'm going to play the game again. How many nodes? Because we have to be able to identify nodes, and this is starting to get a little more complex. So pause the video if that makes sense to you. I'll give you a second. Okay, and we want to count the nodes here. So let's play the same game and color them in as best we can. Okay, so maybe a little quicker this time. So this is all one node here. Let's grab red. We have one node here. Okay. I usually get all sorts of answers on this one, and then I have you come to the board and make you argue with each other in a healthy way. And there's winners and losers, and that's okay. We all get along at the end of the day. Okay. So we got 1, 2, 3, 4, and let's go this kind of pinky purple color that I can never remember the name of. Okay. That's horrible. I'm trying to color it in. I should have made my pen bigger. That's what I should have done. We'll do that next time. Next time I record these videos. So it looks like we have 1, 2, 3, 4, 5 nodes. Okay. In this circuit. A lot of folks kind of look at this one and they forget that, well, if I move from here and I get down here, I don't have to cross over a component. That's all one node. This one gets pretty big. So a lot of times people draw 2 nodes on that. Again, thinking that you're stuck saying that's a node and that's a node and that's a node. It's all one node. Okay? So 5 nodes. Hopefully you got the right answer. You didn't have to pause too long, but I think it's worth looking at. Okay, so here's our circuit. What we want to do is talk about how many loops, and we want to find closed paths in the circuit, and we have to start and end at the same node. So invariably, I get a hand up and somebody says 3 because the first 3 are pretty easy to find. Okay, we have a loop here, right? If I start at this node and then cross over that resistor and come back here, I've started and I've stopped at the same node. I haven't passed through the same node twice other than the start and stop. And it's a closed path. Okay, so that's our first one. Second one that's easy to pick up is maybe that one. Third one that's easy to pick up is maybe that one. Okay, those are the first 3. They're easy to find, but they're not the only loops in this particular circuit because we have other closed paths we can follow. The one that sticks out to me the most, I'll go green here. So I can take 2 of these. I can work my way around here. Okay, that's a closed path in the circuit. I start and stop at the same node down here, and I don't pass through the same node twice. So that's a loop as well. Let's see. Hopefully that yellow's showing up nicely and it's different enough from the green. We can play the same game down here. This is a loop. Okay. Start and stop at the same node. And it's a closed path around the circuit. Last one that I'm aware of, maybe if you see one, throw it in the comments. All the way around the outside, right? Work your way around here. When I follow this loop, I don't cross over that resistor, but I work all the way around there. So to my eye, there's 6 loops in this circuit. Okay, maybe I missed one. You'll let me know. You always let me know when I get something wrong. Please continue to, even though you're not here with me now. Okay, so those are loops. Now, the next bit of vocabulary that we're going to work with is closely related to loops, and that's something called a mesh. Okay. Oops. My notes are up here. I think I've told you that before, but my notes are up here, so that's why I look up here a lot. I got 3 monitors. You're over here for me. My notes are up there, and I'm drawing right there. So that's why I'm looking around a lot. All right, so meshes are very closely related to loops. They're so closely related that I'm going to grab some of my text from up here and repurpose. Ooh, not repurpose it like that. I want to leave it there. Okay, bring it down here, and oops, I'll have to write mesh again. Okay, and say, well, a mesh is a loop. So this is kind of the square is a rectangle, but a rectangle isn't a square kind of situation. A mesh in a circuit has all the same stuff as a loop. Okay, this is same as a loop. The one that's different is down here. And formally we can state it as no intermediate branches, as I remember how to spell intermediate. Okay, no cutting through the infield if you're thinking about a baseball diamond. Let's see, no cutting through the infield. Okay, so if I have a loop that looks like this with nothing in the middle, I can't do this. Okay, nothing in the middle. I hope that's clear to you. We'll talk about it in class when we do live sessions. If not, but I find some people get hung up on this. Still trying to find the right words to make this work. Nothing in the middle. Okay, so let's draw our same circuit again. Come on. Making me wish that I had cut and pasted it. But hey, you want the real experience. This is like we do it in the classroom. I got to draw it over and over again. And I am getting faster with this tablet. My hand will never be the same, but, you know, who cares about that? Okay. So there's the same circuit, maybe drawn a little more shabbily. But the meshes, in some ways the meshes are easier to find. We've got a mesh here, okay, and we've got a mesh here, and we've got a mesh here, okay. So for this circuit, there are only 3 meshes, okay. Those meshes are also loops, okay. All 3 of those meshes are also loops. I had them different colors up here, but those are also loops. But these other loops, the green, the yellow, and the purple, are loops, but not meshes. So when I use the words loop or mesh, I'm usually thinking about which does it apply to. So pay attention to that as much as you can. Okay, that's your anatomy lesson. I'm going to try to do some web work problems. We'll see how that works out for you. And just to make sure that you're keeping up with everything here. And that's your anatomy lesson. We're going to move on and we're going to start combining components because if we have a large complex circuit, we want to be able to simplify it where we can, and we can do that when components are connected in certain ways. Okay, so here's the basic language of how they're connected, and now we're going to add on different ways they can be connected together using this language. So stay tuned and good luck.